let f of x be the piecewise function defined by sine of 2 pi x if x is less than or equal to 1 and x squared plus 4x minus 5 if x is greater than 1. In part A, we want to evaluate and compute the limit as x approaches 1 from the right of f of x and the limit as x approaches 1 from the left of f of x. Let's start with the right-handed limit. So limit x approaches 1 from the right is computed by noticing that for values of x bigger than 1, the function is defined by x squared plus 4x minus 5. And so that's what we want to evaluate, the limit as x approaches 1 from the right of x squared plus 4x minus 5. As x gets closer and closer to 1, our answer is 0. The right-handed limit is 0. Similarly, to compute the limit as x approaches 1 from the left, we note that for values of x less than 1, the function is defined by sine of 2 pi x. So as x gets closer and closer to 1, this gets closer and closer to sine of 2 pi, which is 0. The left-handed limit is 0, the right-handed limit is 0, and that means that the limit x approaches 1 of f of x is defined, it exists, and it is equal to 0. Now in part B, the question is this function, is f continuous at x equal to 1? Now let's recall what it means for a function to be continuous at any value, and particularly at x equals 1. Number 1, f of 1 is defined, must be defined. If it's not, the function is not continuous. So in our case, because the function is defined for anything less than or equal to 1 by sine of 2 pi x, f of 1 is sine of 2 pi, which is equal to 0. So the function is defined at 1. Number 2, the limit as x approaches 1 of f of x must exist. Well, in part A, so what we just did in part A, we showed that the limit exists and it's equal to 0. So in part A, we showed that the limit x approaches 1 of f of x exists and it's equal to 0. The third condition for continuity at 1 that must be true is that f of 1 must equal to the limit as x approaches 1 of f of x. Well, f of 1 is 0. Limit as x approaches 1 of f of x is also 0. So 0 equals 0, and the conclusion is f is continuous at x equal to 1. And let's move to part C. In part C, we want to answer the following question: is f differentiable at x equal 1? In other words, does f prime of 1 exist, or is it defined? So recall that f prime of 1 is defined as the limit x approaches 1 of f of x minus f of 1 divided by x minus 1. Now we know that f of 1 is equal to 0, so the derivative simplifies to limit x approaches 1 of f of x divided by x minus 1. Now because this is a piecewise function And because the pieces switch precisely at x equal to 1, this limit must be computed just like for continuity using right and left-handed limits. So we want to compute the limit x approaches 1 from the right of f of x over x minus 1, and the limit x approaches 1 from the left of f of x divided by x minus 1. If both of these limits exist and if they're equal, then the function will be differentiable at x equal to 1. Let's start with the right-handed limit. So we want to compute the limit as x approaches 1 from the right of f of x divided by x minus 1. For values of x bigger than 1, f of x is x squared plus 4x minus 5 divided by x minus 1. As x approaches 1, the numerator approaches 0, and so is the denominator. This is an indeterminate form. We know how to handle that. This is limit x approaches 1 from the right. We factor the numerator into x minus 1 times x plus 5 divided by x minus 1. X minus 1's cancel. We're left with limit x approaches 1 from the right of x plus 5, which is equal to 6. So the right-handed limit exists and it's 6. Let's compute the left-handed limit. We want to compute the limit x approaches 1 from the left. Now for values of x less than 1, the function is defined by sine of 2 pi x, and this is divided by x minus 1. As x approaches 1, the numerator approaches sine of 2 pi, which is 0, and the denominator also approaches 0. We make the following substitution. Let y be x minus 1. Note that as x approaches 1 from the left, y is going to approach 0 from the left, because if we take values of x close to 1 but smaller than 1 and subtract 1 from those values, we're going to end up with small, very tiny negative numbers close to 0. So y approaches 0 from the left. And if we solve for x, x is equal to y plus 1. Now let's rewrite this limit in variable y instead of variable x. So this limit becomes the limit y approaches 0 from the left, sine of 2 pi times y plus 1 divided by y. So let's write this as limit y approaches 0 from the left, sine of 2 pi y plus 2 pi divided by y. Let's use trig identity. The trig identity that we're going to use is sine of a plus b equals to sine of a times cosine of b plus sine of b times cosine of a. So this becomes the limit y goes to 0 from the left, sine of 2 pi y times cosine of 2 pi plus sine of 2 pi times cosine of 2 pi y. Now divided by y. Now note that sine of 2 pi is 0, so this part is 0, and cosine of 2 pi is 1. Therefore the limit simplifies to limit y approaches 0 from the left of sine of 2 pi y divided by y. Now next thing what we're going to do, multiply the numerator and denominator by 2 pi and rewrite this as 2 pi times the limit y approaches 0 from the left of sine of 2 pi y divided by 2 pi y. Let's make one more substitution, and that substitution is going to be let z equal to 2 pi y. as y approaches 0 from the left. 2 pi times very, very small negative numbers will also yield small negative numbers close to 0. So we can conclude that z also approaches 0 from the left, and the limit in variable z becomes 2 pi times limit as z approaches 0 from the left, sine of z over z. We know this limit. It was shown in an earlier video that this limit is 1 times 2 pi, which gives us 2 pi. So the left-handed limit is 2 pi, which is over 6. It does not equal to 6. So we had the limit as x approaches 1 from the right of f of x minus f of 1 divided by x minus 1. This limit was equal to 6. And we had the limit as x approaches 1 from the left of f of x minus f of 1 divided by x minus 1. That was equal to 2 pi. That's close to 6, but it isn't 6. So the left-handed limit and the right-handed limit are different. They're not equal. That says that we have a corner point when x equals to 1 and the derivative does not exist. The conclusion is f is not differentiable at x equal to 1. For more videos, visit www.mathprepvideos.com.